Hello, and welcome to the course Digital Expertise 2. My name is Rodrigo Cofre. I am a permanent researcher at INRIA, the Institut National de Recherche en Informatique et Automatique, so National Institute of Research of Informatics and Automatics. So let me start by saying a couple of words about me, that the teacher. So I'm a very enthusiastic computer scientist and neuroscientist. So my research is about the brain, and I've been studying during the last years the brain in different stages of consciousness. So what happens with the brain goes into the state of total unconsciousness, like the one induced by general anesthesia, or deep sleep, the comatose states, or what happens when we dream, or when we meditate, or when we are under the effect of psychedelic drugs. So all these states of consciousness during the last years have been studied scientifically thanks to the digital tools of neuronal recordings. So fMRI, like magnetic resonance imaging, electroencephalography, structural imaging of brain networks. And for that, we use a lot of digital systems, but also a lot of mathematical tools. So about my background, so I have a master's and PhD from the Université Côte d'Azur. I did my PhD here at the INRIA Institute. And then I did a first postdoc in the Faculté des Sciences en Physique Théorique, so in theoretical physics at the Université de Genève on Switzerland. Then I came back to my country as a professor at the Université Valparaiso. But then I decided to come back to Europe and work again at the Institute of Neuroscience in Paris. So over there, I participate in a lot of new research, and then I got my grade of HDR, which is Habilitation de diriger de recherche, like it's like a second PhD, something like this, that we do here in France in order to be able to have PhD students. And then I was part of the lab of theoretical physics also at the École Normale Supérieure here in France. And then I got my permanent position here at INRIA at the Université Côte d'Azur. So I'm very, very happy that now I'm established. Now I settle down here in Nice as a researcher mainly. So I am not a professor in a way, so my job is mainly to do research, but I'm allowed to do some teaching and participate in master programs. So I'm very happy to be your professor. But I wanted to let you know that my background is kind of different. I'm not used to teach teachers, not students in this subject. So, but I wanted to tell you anyway that I have some background in teaching, mainly mathematics, physics, and neuroscience, and signal processing, modeling in neuroscience, and now scientific communication as well at the Université Côte d'Azur. During my time at the Department of Theoretical Physics in Geneva, I was teaching mathematical methods and mechanics. But during my time in Chile, also modern physics, engineering, and theoretical neuroscience. to students in different years in the bachelor, but also in the master's and the PhD programs as well. So please don't hesitate to contact me if you have questions about this course. I will be happy to answer. Probably not in the first 24 hours, but I'm very keen to be as useful as possible as your teacher in digital expertise too. So let me start with the course, and let me start with a fundamental aspect of computer science, which is the idea of language. So what's the difference between a message like the one you see in your screen on the left part, which is an absolutely clear sign that has a very precise meaning, and it's even internationally accepted as a stop sign. So when you see that and you are in a car, you have to stop. So no space for interpretation. So this type of message, it's very pertinent for a special situation, which is how to regulate ourselves to go and use dangerous machines like cars, but at the same time, very useful ones, no? So how we communicate in terms of producing the right norms and the right laws to enforce behavior, in this case, to humans. On the right, we have a very interesting, mysterious message that is given in the context of art. So what want the artists say? And this ambiguity provides richness in terms of what the artist wanted to say with this art. And it's a natural language. It's a language in which we communicate in order to communicate emotions. And it's an extremely rich alternative to the alternative we have on the left, which is an absolutely clear but a poor message in terms of emotion or what I can say with just design. So I want to emphasize here this difference. So even very precise language, like the language of mathematics, in which I can express very clearly a problem, but at the same time, I can even solve the problem within the same language. So that's very important and very unique about a mathematical language. It helps us to formulate problems, but also to solve them. And even when you solve them, you need to be very clear about the limitations of the language of mathematics. The interpretation can be problematic. So look at this case. So we have the following problem. Imagine that you are in the surface of the planet Earth and you want to go to the moon. And you want to do that by folding a sheet of paper like the one I have here, for example. Okay, so what's the width of this paper is 0.01 centimeters. And the distance from here to the moon is 384,000 kilometers. So I have to fold my sheet of paper, and that will give me, now it's 0.02 centimeters, okay? I will do it again. If I do it again, now the width of my paper is 0.04 because I have four. I will do it again. And I have now 1, 2, 3, 4, 5, 6, 7, 8. Again and again. Question that you can solve just using mathematics. How many times you have to fold this paper in order to cover the distance from here to the moon? Well, this is a problem that children in the school can solve because actually you don't need very sophisticated mathematics to solve it. It's just you use this exponential rule, 0.01 to the power something will give me, it's equal to 384,000 kilometers. And the answer is quite surprising. So it's just 42. But what's the problem? The problem is that a real paper cannot be folded more than 7 times. So let me come back here. If you solve this problem just using mathematics, it will give you, okay, you have to fold it 82. Sorry, 42 times, which is a kind of easy things to do if you don't take into consideration the real physics about this. So I folded once and it took me 1 second. I folded twice, another second, 3 times, 3, 4 seconds. And I'll say, well, in less than a minute, I covered the distance from here to the moon. And that's what mathematics says. But you have to take care about what does it mean in terms of implementation, because no one can do that in practice. So what theory says is not that what practice says. Another example in this line is kind of the opposite problem. So imagine that I have 2 objects separated by 1 meter. So probably something like this. And the exercise is the following. Imagine that at each step, I cover half of the distance that's still remaining. So in the first iteration of this exercise, I have still remaining 1 meter. I will cover half of the meter. And in the second iteration, half of what's remaining is 1/4. Then half of what's remaining is 1/8. And then 1/16. And then 1/50. 1/60, 1/128, so on and so forth. So the question here is when the distance will be 0, meaning that the 2 objects are not separated anymore. But here, no matter how many steps I've done in my iteration, it will always remain a positive number. It can be extremely small. But then divided by 2 will be even smaller, but still positive. So I will never reach the other object. But again, in reality, what physics says is that when 2 objects are separated by a distance which is smaller than the atomic distances of the nucleus, the 2 objects are actually touching each other. So there is nothing in the mathematical equations, no matter how precise and logically based are, that tells you that there is a constraint, which is physical constraint, that means that even if there is a positive number, the objects are actually touching each other. Let me give you another example. This is the example of the 2 envelopes. Imagine that I have 1 envelope with a given amount of money, But at the same time, I will offer you to participate in a kind of fair game, which is the following. So either you open your envelope with a certain amount of money, let's say 100 euros, and I invite you to participate in uh, the following game or exercise. So it's either you take this or you take this other one. But this other one inside this envelope is either half of what is here, so 25, or there is 200 euros. So either you take this one with 100 or you participate in this game of getting this new envelope with either 25, which would be a bad uh, outcome, or 200, which will be a very good uh, output. What would you choose? And here the mathematics is very clear. It says that on average, what is better for you is to take the risk, because there is a very basic mathematical operation that is with one half probability, with 50% probability, you will have x divided by 2, whatever x is, meaning that in this, I gave the example of 100 euros, but it can be any other um, amount of money. On average, with 50% of the probability, you will have x divided by 2, so half of the money, and with half 50% probability, you will have twice the amount of money that is here. And on average, it gives you 5 divided by 4x, which is bigger than x on average. It doesn't mean that in if you participate in this, you will be benefited, you will win, but says that in general, the mathematical rule, the mathematical consideration is go and play. That is not taking into consideration your particular situation. Let's say it's not the same, let's say $1 million, which is a lot of money, let's say. But with $500,000, it's a lot of money as well, but it's not covered, for instance. Yeah, I don't know. Imagine that with $1 million, you are okay for the rest of your life, and with x divided by 2, you're not. And probably 2x, it doesn't really compensate for the risk of, let's say, having $1 million. So, and here the mathematics don't care about x because it's just a variable. What I wanted to say here is that you need to take into consideration that there are humans in the loop, and mathematics don't take into consideration that. And the last example is the example of Sally Clark. It's a real example. You can Google it. It's a real example of bad use of mathematics. It's a mother of at least 2 children, and both died spontaneously from one day to another with no explanation, no medical explanation. So she ended up in the court, and the judge says, well, there is a 1 over 20,000 probability that your children would die without medical explanation. But you have 2 children, and both of them died without medical explanation. So you probably did something that was not detectable by the medical doctors. And the probability for that to happen, it's 1 over 400 million. So whatever type of excuse that you are going to say to me, I will say, well, it's so unbelievably improbable that I will not um, believe in you. Wrong, wrong assumptions. So she may had a genetic condition with a certain proclivity of their children's to die, and both of them may have exactly the same condition. So here, when you multiply two probabilities, you are assuming that these probabilities are independent, which is not the case. So fortunately enough, this argument was put forward, and she ended up getting out of jail. And of course, this was a big debate in the mathematical world, but also in the legal systems, in order how are we using these tools in this context, because can be extremely problematic. So the main point of all these examples, which belongs to my, let's say, expertise, which is mathematics, is just to tell you that when even very clear languages, very formal languages, like the language of mathematics, when it comes, when it interacts with human behavior or the human experience, can be extremely problematic, and even with ethical implications. So there are two kind of languages, let's say, and in this context, I would like to contrast the English language, but actually, it's not really about English that I want to talk about. It's like any other natural language that we use to communicate. It can be French or Chinese or other language. And a formal language like the language we use in Python programming language. And what are the commonalities? Is there a boundary between the two? What are the purposes of one and the purposes of the other? And we will see that there are different kind of languages, both with their own advantages and disadvantages. And let's see about that. So both languages, natural and formal, will have rules or syntax, and also semantics and meaning. So the words have a meaning, and the words belong to the grammar, let's say. You need to respect that. And we will see that for English, even if you don't respect the grammatical rules, still the meaning is there. For formal languages, we don't have that. So both allows us to communicate, probably and usually, to different populations. One is to communicate between humans, and formal languages between humans, but also and especially to machines. And machines are very good for some specific tasks. So I will not compete, not even as a professional mathematician, in a competition with a very basic solar calculator in order to see who is more precise or more quick to solve a three-digit multiplication. So 347 times 264. I will not dare to compete with the machine. The machine will make no error. Probably I will. And it can take me, let's say, 1 minute to solve that. And the machine will be less than a second. So machines are better than us for some specific tasks. and humans, we are better for all the type of tasks. So it's not about who is better or who is worse. It's really the question is about what, what in which context. So the definition of a formal language is the ones we use in informatics and in computer science in general, is a set of strings, which means a finite sequence of symbols built from an alphabet according to specific syntactic rules. For example, the language, formal languages is the one we use in Python, C++, JavaScript, and other programming languages. It allows us to write logics and mathematical formalisms, like the one of propositional logic or regular expression, regular automata. And you can define them mathematically. There's a whole branch of pure mathematics that is about formal languages, like what are for instance, the questions that they ask is, are these two languages equivalent? Can I write this type of code in this language, but also in this one? Are these compatible? Or the capabilities of this language is much larger than the capabilities of this other one. And today, thanks to the tools of LLMs, large language models, you can write a program in one language and translate it into another language, but sometimes there are some misspecifications, and that for computer scientists can be a very big issue. So what's the definition? So language is a set of words that belongs to the set of words where W, so the words follow the rules of a certain grammar that is defined in the context of the logical formal language. So among the many features that this language have is that they have a very strict syntax. So every symbol matters. So you can have in an essay and in English, let's say a grammar fault, and still, I mean, you can still convey the main message. The problem with formal languages is that they don't allow that. So the program output will be error. So you will have nothing from that, even from a grammatical fault. Which if you just type, or you miss one parenthesis, or you miss one point, or you miss one A, completely different, or either error or not what you expect to have as an output. They have unambiguous interpretation, so that's very important for the formal languages. So when you write a word or a command in a computer program, it's not that some days, if the computer is happy, will give you something, and otherwise, depending on the mood of the computer, no. It's just an ambiguous interpretation. You have a well-defined semantics. One can say the same for natural language, but here is even more strict in the sense that if it's not exactly right, it will have no meaning and again, error as a message of the computer program. And they're really designed, even if you can communicate with humans with this language, it's really designed for computational or logical reasoning and essentially no other things. It will be extremely difficult, and I would say even impossible, to write a novel in using this language is extremely poor to communicate, again, emotions, situations, real life uh, scenarios. So a natural language, what is a natural language? Like the one, the English, French, Chinese, even they evolve organically among people. The way in which young people is communicating is not the same as the old people, or formally, if you are referring to a boss or to a professor, it's not the same. Communicating among your peers, children, let's say. It is ambiguous, which can be a very rich property. It depends on the context, and that's the main, let's say, richness of humor. Let's say it's when out of context you say something and can be extremely funny. So you make jokes using natural language. If you don't make jokes using programming languages or formal languages, even if sometimes you can, if you're a super nerd and understand, let's say, the details of these languages. It can be flexible and metaphorical, so it allows poems, let's say, all this beautiful uses of language. And it's rich in redundancy, which is something you don't want to have in a computer program, and emotion, which is an extreme richness of our human nature. How can we express and even language? You need to really master language in order to convey properly emotions. So let me give you an example of a phrase in English. So all men are women, and all men and women are invited. So this is an ambiguous statement. Why? It is all men and women that are invited. So if you are a man, you need to be old to be invited. Or it means that both. It doesn't matter if you are a man or a woman, but you need to be old to be invited. So in the first interpretation, you can be a young woman, but you need to go with an old man, or not necessarily, because all men are invited and women are invited. But in the second interpretation, again, it doesn't matter if you're a man or a woman, but you need to be old. What does it mean, this phrase? You know that it's ambiguous. So you need to be precise here. I'm sure that you have seen in internet this kind of mathematical exercise. So, like, how much is 2 plus 2 times 2? And you can say, well, 2 plus 2 is 4, but times 2 is 8, or is 2 plus 2 times 2. In this case, it's a very bad example because the answer is the same, it's always 8. But you see the idea, no? At least in mathematics, we have hierarchy and rules in order to operate numbers. So it's from left to right, and it's the parentheses, and then the multiplication comes first, and then the summation, and rules like that. But in English, well, you can still be slightly more precise with the parentheses, but still, if you just put this sentence, is completely ambiguous. So how to disambiguate that? Well, with a formal representation, which you can use to disambiguate. So you are invited if you are an old man, and you are invited if you're a woman. It doesn't matter how old are you. And in the second interpretation, you're invited if you are old and you belong to the sex men union woman. You know, here we are using this Venn diagrams of union, intersection, these kind of things in order to be very precise in order to explain this to a computer. And that's the whole game. How do I explain this problem to a machine that is incapable to understand context, to understand anything which is out of the realm of. This can be very frustrating. We have seen all probably videos of people getting mad to the computers, even myself sometimes. I get mad at computers. How you don't understand this very basic example that I'm giving on this very basic of why are you giving me errors if it is absolutely clear what I'm saying. And sometimes there is a point missing or it's not well indented. That it's usually a problem in Python, or it's yeah, you made a grammatical mistake, and that's give you a complete error. So it's frustrating to try to communicate with computers. Of course, now with artificial intelligence, the boundaries between natural languages and formal languages are more and more diffuse, and it's more and more user friendly now. The whole realm of design, human computer interfaces are more and more user friendly. Now we have these iPads and iPhones that you just touch the applications, and the application will open, and you are allowed to make mistakes because the machines on the back end they solve the problem. So in a way, it's more and more user friendly, and it's something that we really take care of in the development of new software tools, but it's still difficult to write informal language because we often forget that machines don't understand context and do not allow any type of grammatical mistakes in the sense of formal language. So just to make a contrast or difference, we have seen that important aspects of the languages are syntax, semantics, so meaning how they tolerate ambiguity, what's the natural evolution of those languages, and what's the main purpose. So just to come back to the difference of the syntax in a formal language, it's explicit and very rigid. In natural language is flexible and depending on the context. Again, young people communicate in a different way that old people and things like that. Semantics, it's extremely precisely defined by an interpreter or compiler. In natural language, it's implicit. This as explicit comes as in formal language, and it's context driven. So the main, even the meaning of a same sentence can depend on the context. That's the whole skill of a humorist, for instance. It's to say the same thing but in a different context in order to make it funny. This kind of thing you cannot do humor again in formal language. You know. So how they treat ambiguity? There is no ambiguity in formal language. Otherwise, it's detected as an error. So you're not being extremely precise in what are you telling me. In natural language, it's can be frequent and it's still okay, and it's always and it's often deliberate, as in the case again of politicians. They are experts in saying the same thing in order to mean two things at the same time, in order to try to convince everybody that they are right, not just on their own political, let's say, trench, but in the whole spectrum of the political ideas. How they evolve, formal languages are very designed and arbitrary in a way. So it's the programmer, the company that is owning the programming language that they decide how these languages will evolve, what are the new features, and things like that. They are designed. Even the most recent LLMs or artificial intelligence in general, they do not evolve naturally. So there are companies like OpenAI, or the companies behind DeepSeek, and the companies behind Cloud, just to make some example, or the French, it's called Le Chat, and they decide, they deliberately put new features or erase things that didn't work or try to promote the use of some new tools, but it's design. But how natural languages evolve, it's much more emergent or evolving, but naturally. So even if I invent a new word, probably will not proliferate as much as if everybody start to use this word, but it's very difficult. So that's why it's emerging in the sense that if several people are constantly using this new word or this new center or this new way to communicate, it's because probably it's reflecting some deep needs in this community to express themselves in that way, and probably will propagate naturally. Now it's more easy with the social networks, but it's not just design or standardized or arbitrary as it is uh, with the evolution of formal language expressions. The purpose of a formal language is precision and computation. Again, you will not write a poem or a novel using formal language because the whole purpose is different. It's different. But in a natural language, it's expression of ideas or emotions or communication or persuasion. I want to, yeah, it's very difficult to try to convince someone to buy an included product using natural language. Sorry, using formal language. Much better to use natural language. So these are mainly the differences in syntax, semantics, ambiguity, evolution, and even purpose of these two kinds of languages. So let me illustrate some classic error. Here is Python, but in general, all programming languages will not understand sentences like if parenthesis equal x, which is a variable, is equal to 5, which is the variable is taking the value 5. Like this is an error, even if it's absolutely clear that I want this program to take an action if my variable is equal to 5. So if I say that in English, it's understandable. If, and I'm using here even the same word, if my variable takes the value equal to 5, do something. Well, here is a technicality. If I want my variable to take a value, I make it x equal to 5, but if I want to verify if my variable, if I want to assign the number 5 to my variable x, I put x equal to 5. But if I want to, for instance, verify if my variable is taking the value number 5, I have to ask if x is equal to 5. But it doesn't matter. What I want to say here is that if I don't close here the parentheses, the sentence is incomplete, and the computer will give me an error. You see the difference between a formal language and a natural language? You see, in natural language, I can make a clear grammatical error, or in syntax, let's say. Me go store now. That's absolutely incorrect. If you do that in a test of English, you will fail. But if you say that to someone that is capable to understand English, a human will understand that the meaning of that phrase. So one is flexible, one's inflexible, one it's more natural to express a sentence, and another it's more like it's for a purpose of computing and computation. Let's put another example in the same lines of what's different between a logical language, a formal and natural language. For instance, this is a very general expression in formal language. I want to do not. I want to not the parenthesis P and Q. And there are mathematical rules of logic that tells me that this is equivalent to apply this not to every symbol. So it's not P, then not and, which is an or, and not Q. So it's not P or not Q. So how does it look in English, that a natural language? It's not the case, for instance, that both, because it's an and, Peter, P, and Quentin are coming. The problem is that even if it's that informal language, it's no ambiguous, and it's no place for ambiguity, because these are the rules of logic. These are the rule of mathematical logics.